when I got ready to come here, I had 2 boxes of Class C. First, I had a large box of Class C, and I was going to sort through that and see which I was going to use in the seminar. And then, so I did that, and I put them all in a box. And then I found another box of Class C, and I thought, oh, there's some other things that I might want. So I make a second box of perhapses, you know. The perhapses got brought, and the main box did not.
Oh no.
So but we're going to make do. We're going to have some stuff. So here's what we're going to start out with. Most people think they understand what a spark is. And so if you have a cigarette lighter, it makes a spark. If you drag a chain behind a truck at 50 miles an hour on a concrete road, it makes sparks. If you have electrical shorts, they make sparks. So we use the word spark for things that are pretty different from each other. So we're going to talk about what they are and what they are not, what generates them, and do they come in different colors, and how are they used in fireworks, movie, and stage effects. Now, Joel and I have been friends for years, and he is an expert pyrotechnist. By the way, how many of you could tell me the difference between a pyrotechnist and a pyrotechnician? The terms are used almost interchangeably by some people.
Art and work.
I think there'd be a lot of pyrotechnists that would say, hey, there's a lot of work to being a pyrotechnist. Many pyrotechnicians are also pyrotechnists and vice versa, but not all. A pyrotechnician is someone who can set up a show and knows where the motor rack should be and how they should be oriented, and knows how the electrical firing system works, and can plan shows to a degree. And he has to have a lot of knowledge about techniques, but he's essentially an engineer. Okay, a pyrotechnist is someone who really understands what's underneath the paper, who knows something about the chemistry, something about burning temperatures, different kinds of metal powders, different kinds of chlorine donors, and so on, and can fine-tune a composition so it does what he wants it to do. So they're not the same person. A lot of pyrotechnists really don't know much about what's inside of a shell, and there are some pyrotechnists that you wouldn't want to hire to set up a show. Okay, so I mean, I'm not trying to put one of these activities above the other. They're both necessary, and they complement each other. How do I go to the next slide? How do I go to the next slide? Oh, it's complicated. All right. So, what do you suppose the largest known spark is? I said, okay, I want to go see the largest spark that's ever been produced. Well, in Oklahoma in 2007, there was one that was over 200 miles long.
Glimmer. I wonder how far the thunder.
I don't know how far the thunder was heard, but it was a lightning strike, and lightning discharges are indeed sparks, but they're not pyrotechnic sparks. Doesn't mean they're not energetic or not potentially lethal, but if you ask the question, what's inside of an arc, or what's inside of a spark, you get the physicist hand waving a bit. The general consensus is that at least some of what you see in a spark is plasma. And plasma is atoms that have had their electrons stripped away. Okay? And they behave very differently than atoms that are prepared to bond onto other things with electrons. A plasma spark can be a 1/4 inch long or less, or it can be 6, 7, 10, 20 inches, depending on how you set it up. And they're spectacular, and they make noise, but they're not used in pyrotechnics. The star is burning, generating heat and gas, and it's throwing out little particles of aluminum or titanium or iron, whatever it is, and they're reacting with the atmospheric oxygen and becoming real visible. And we're gonna do that in a big way here when I'm done with the PowerPoint. Microstars in fountains, and a lot of the Class C stuff, you know, you light it, it's crackle, crackle, crackle. And those aren't really sparks; those are little stars. So a spark, any of a collection of localized light emissions of a transient nature. Okay? Pretty broad definition. Electric spark, a short duration flow of electronic current across a gap between 2 points. Commonly, such sparks are produced by static electricity. So you walk across a carpet and you touch a light switch and you get a spark, and you feel it, and you see it. Sometimes so the gasoline vapor is being ignited by an electric spark. But pyrotechnic sparks can also be incentive. So again, incentive sparks aren't a very specific, narrow kind. But it's well to remember that some sparks are not particularly incentive. They're too small, they don't have enough heat. So you can take a sparkler, and I'm going to do this, take a sparkler and hold it against a piece of Kleenex. Not so the wire touches the Kleenex, but so the sparks land on the Kleenex. And it won't ignite the tissue paper. And that's because iron is used in sparklers that it's pretty fine. And the things that are coming off are really small. They don't have that much heat. That's why you can put your hand, you can hold a sparkler like this, and the particles will fall on your wrist, and you may feel them, but you don't get burned. Unless the sparkler is made in India and they have magnesium on it. And I had one of those I was going to demonstrate. It's a sparkler made in India, and they take a kind of ordinary steel sparkler and they dip it in some sort of adhesive and they roll it in pretty coarse magnesium. And it makes an interesting spark. You have steel and then you have magnesium sparks, which if they hit your hand, you'd know it. All right, so pyrotechnic sparks can be solid or liquid. They're generally heated in a flame and are ejected from the flame, and the particles glow. And I've had a conversation with friends. They said, well, if you stir up a campfire, you know, you got a nice campfire, and somebody goes in there and they throw a log in or they stir it up, and you got a whole bunch of gold sparks that go in the air. And somebody said to me recently, I can't remember what it was, well, those aren't sparks, those are embers. I said, well, we usually think of them and call them sparks. And I said, you take an ember, say you take a piece of charcoal, you take it on a charcoal fire, it's all gray, it's all covered with ash. You grab it with a forceps, bang off the excess ash that's, you know, and it's glowing dull red. Now, if you threw that out of a window from a skyscraper, or you threw it out of a window of threw it out of an airplane, and you could see that, it wouldn't give off a lot of light, but you could probably see it from some distance away. And you might be confused a little bit whether that's a spark or not. I would say no, it's not a spark. That's an ember, a glowing ember. But when you stir up a campfire, it's not all that different. It's carbon going through the air, but it's being really oxidized and glowing bright, and that's why you see it. So it turns out that lots of carbonaceous materials are capable of creating low temperature sparks. Wood, paper, organic dust, many other materials, and we'll throw some into a flame. And because they're small and they're brief and they go off light, they're sparks. So here's a pyrotechnic spark. Where's my technician? Is he here? Here. none of you.
The audio.
Yeah,
Audio technician.
I'd like to eliminate that. It's not on the screen.
No, that's
Wonderful,
your-
wonderful.
that's your-
Okay. So here we see a picture of a burning composition. There's a flame envelope, but everything isn't consumed in the flame. Now there are some pyrotechnic compositions where nothing gets out of that flame envelope. It's too reactive. So if you light a piece of magnesium ribbon, it's hot as hell, and there's not much sparks produced. There's a ball of burning magnesium. However, other kinds of sparks will be ejected from a flame envelope. Now here's what we think of as sparkler. It's not only sparklers of light, we have to just look at the picture. But look at what's happening. There's a flame envelope in the center on the wire, and it's ejecting particles, but look what's happening to those particles. They're just not ejecting and falling by gravity or being propelled because they're burning. But they're branching. In fact, a lot of them look like they're exploding. They look like little miniature shells. And so I've been asking a lot of people, what causes sparks to branch? Well, it turns out there are lots of kinds of sparks that don't branch. The ones that are really good at it are iron and steel, particularly iron and steel that has a lot of dissolved carbon. So high carbon steels, but even low carbon steels will branch. Cast iron makes wonderful branches. And so here we see a typical iron branching spark. Now here's another picture of a sparkler showing branching sparks. And it's just a little closer up, slightly out of focus picture that shows what we mean when we talk about branching sparks. But the thing that I find frustrating, and I've talked to some people recently about this, what exactly causes the branch of the spark? And why do some metals do it and other metals don't? Iron is really good at it, but titanium doesn't as well. Well, I had a theory that said, well, okay, the carbon is dissolved in the molten metal, it's hot, it's getting hotter, it vaporizes, probably makes carbon dioxide or other carbonaceous gases, and they're hot, and we all know hot gases expand, but they're enclosed in a steel globule, and they break it. Okay, so that's a nice theory, but I don't think it holds up necessarily, because titanium doesn't necessarily have any carbon dissolved in it, and it branches very much the same as steel. So there's other possible explanations, but you try to Google this, you try to talk to chemists about it, they immediately start the hand wave, because it's not really been studied. They can tell you what kinds of steels make what kinds of sparks. And for example, stainless steel doesn't make much branching sparks. Cast iron makes beautiful branching sparks. But if you say, why? You don't get a good answer. At least if anyone has good answers, I should certainly be interested in hearing them.
I got a question. Would nickel and cobalt make branching sparks since they're closely related to iron?
They might, and I don't have an answer.
I guess I'm nickel and cobalt to try it.
Manganese. I'm going to turn this on.
Manganese is next to iron in the periodic table, and
It's further left.
It's to the
iron,
left.
Nickel, cobalt.
Well, it's near it at any rate, but it's the same color, but it doesn't branch very much. If you had to use it, you could use it, but it's not as good, because I have looked at that.
The best branching sparks of any metal seems to be iron. And most things that we think of as sparks have iron involved. There's various iron alloys that spark pretty well. Yeah?
What about mish metal? You know, the little striker.
Lanthanide metals.
Well, mish metal is a metal of cerium and guess what? Iron. And pure cerium is soft and malleable and doesn't make much sparks. Now, I don't think you can get cerium powder. Can you? Pure cerium powder? I don't think it's powder.
Several years ago, somebody had a rod of cerium about that big around and a foot long here, and it made nice sparks cutting it with a hacksaw.
Yeah, but there's.
And I don't remember if they branched or
Yeah,
not.
the problem is there's iron. Usually
No,
when there's
this was cerium,
the-
not
in the
metal.
hacksaw.
It was
use a
cerium.
hacksaw.
Yep.
There's iron in the hacksaw.
It was not metal. It was cerium,
Okay, but
and
if you
it
cut
made
it,
sparks.
but if you cut it with a hacksaw, there's
It was
iron.
making sparks. Well, there'd be
There's iron from this cutting,
from the blade.
from the blade. So I mean, you may be right, but cerium by itself might make sparks, but that test doesn't tell me for sure. Now the next picture shows a drawing from the Encyclopedia of Pyrotechnics, and Ken Kosanke drew or had drawn, and it's just a drawing showing of branching sparks. But notice it may branch more than once, and sometimes there are some sparks that can branch as many as 3 times or maybe more. So here's a photograph of a branching spark. So A is the first spark that's branched, and you follow line V out, and it goes out of the frame, but it eventually branched. C branches twice. And so you have a primary branch, a secondary branch, and a tertiary branch. And this is the kind of thing you see in sparklers. How do I go back?
Question for you.
Huh?
Audiovisual man, please.
Try the arrow.
Arrow, back
Try
arrow.
the back arrow.
Back arrow.
Aha. Thank you.
Well, you're still going forward, stuff we've never seen. There you go. Oh, there you go. Huh? Yeah, he was going back.
I was going back, yeah.
Yeah, you were.
Okay, here we go. All right, so now a lot of pyrotechnics can, if they're close up, if you're looking at them from 10 inches or 20 inches or 3 feet away, you'll be impressed with branching sparks. But if you make stars for a 3-inch shell and you light one on the ground, you think, oh, that's gorgeous. So you put a bunch in a shell, you're going to be disappointed because the individual bursting sparks don't give off that much light. And when you're looking at it in a dark sky from 200 feet away, they're not that visible. So you can find formulations for steel stars from the late 1800s and early 1900s, and for maybe for some fountains or Class C's they might be usable, and generally steel powder is not used for aerial fireworks for display fireworks. Now, this is just a discussion of more branch sparks. And one of the things is not only does titanium branch, but magnesium branches to a certain extent. And quite counterintuitively, carbon branches by itself. So there's a phenomenon known as the flower pot effect. And there's also a Japanese sparkler which is called Cinco Hanabi. And I brought some, except they didn't get taken. I was going to demonstrate them. But branching sparks can be caused by pure carbon, by all kinds of steel and iron alloys, pure steel, titanium, and to a lesser extent magnesium. And all the different alloys will produce different ones. So there's people who have studied sparks, and it's even an analytical technique. You've got something you don't know what alloy it is. What they used to do before the chemists came up with really sophisticated and very accurate analyses, you could take some unknown metal and abrade it with a wheel and make sparks and identify what kind of metal it was. So here we see a picture that shows, wrought iron, mild steel, steel with half to less than 1% iron or carbon, high carbon steel, and some of these others are kind of like stainless steel. Can you make colored sparks? Well, a lot of pyrotechnic enthusiasts would say, "Oh, of course you can make colored sparks," but they're not sparks really; they're stars. So when you see a fountain that has beautiful little red and green and blue particles coming out, those are little microstars. They're not really sparks. Now, you can make gold sparks, and if you have a lot of carbon in a spark, it'll make it gold. If you have a lot of iron in the spark, it'll make it gold. You can make white, and you can make off-white sparks with aluminum and titanium and magnesium and magnesium. But a true spark, if you see really good color, chances are it's not a true spark, it's a star. Now, iron has been used in fireworks through antiquity. I found this picture, I think it dates from about the 1700s, but cast iron was used by the ancient Chinese in fireworks. Who invented guns? If you ask who invented gunpowder, everyone says, well, the Chinese did that. Well, did the Chinese invent guns? Not really. The first time the Chinese saw cannon was European cannons. But the Chinese had invented effective powder that would shoot rockets, and they could make stars, but they hadn't quite figured out how to burn it fast enough that it could be used as gunpowder. And you can make steel fountains 3-4 inches in diameter. They have a tendency to explode, but it can be done. And frequently they're with relatively mild compositions. They're not even black powder. They're like potassium nitrate and red gum, and they're core burning. But the iron is making the sparks. Now here's a here's a wire sparkler composition. And there's a couple things to note here. Barium nitrate, over half the composition in the first formula and almost half in the second is barium nitrate, not potassium nitrate. Potassium nitrate's absent in Formula 1, but there's a little bit of it in Formula 2. Now, there are dozens and dozens of steel wire sparklers, but they all work very similarly. And the reason for the barium nitrate is that it has a high melting point, and it's got aluminum in it. See the aluminum? Several grades in some sparklers, but relatively small percentages. And the reason for this is that it's an energetic fuel. It heats up the flame, produces lots of gas, throws the sparks out. Because you could oxidize iron on a wire with a really cool burning thing, but it wouldn't throw the sparks. So the aluminum energizes the sparkler mix. Iron powder is in the first one. Steel filings, okay, but steel is mostly iron. Okay. Notice it says neutralizer. Well, the problem is that aluminum powder, if it gets alkaline, tends to react. And so when you make sparklers, they usually put some boric acid in. There's other things you can use that keep the solution from becoming alkaline. And sometimes they're concerned about the rusting of the iron. So if you have a sparkler that you bought in 1935, chances are it's not going to work very well unless you have vacuum packed it. Okay, and because the iron is going to rust, and iron oxide, under most circumstances, doesn't make any spark. I'll give you an example where it can be used. Now here's a standard sparkler. Now, you know, you've all lit sparklers at one time or another. So if somebody asks you, why is it so hard to light a sparkler? You got to roast it into submission. And if you just try to light a sparkler with a regular match, you may fail. Well, it can be done. I've done it. But you have to hold the match just right, and maybe use more than one. But here's the sparkler, and I don't know whether you can see this very well. The tip of the sparkler is slightly different color. It's been tipped in a prime. And there are sparklers they make like that, and the sparkler composition itself takes a lot of heat because barium nitrate has a high melting point and even a higher boiling point. And you've got to break up that barium nitrate. You just can't leave it as a solid. And there's aluminum there, but you've got to get it started. You've got to heat that up. Barium nitrate is a very good oxidizer. You can make powerful flash powders with it. You can make really wonderful stars with it. But you got to be careful because it's very easy to make stars with barium nitrate that will go out and won't burn from a lift. Here's that sparkler I mentioned that made in India with coarse magnesium on it. And if you hand that to a little kid and he's holding the sparkler up like this, those magnesium parts are going to come down, and they're sparks, but they're hot, and you know, and so you don't see this made in this country. And whether they still make them in India, I don't know. But sparklers are now legal in most states, I think. When I was growing up in Minnesota, you couldn't buy sparklers. You know, you had to go to South Dakota. Now Minnesota has loosened up a little bit, and I don't know that there are any states. Gary, are there any states that ban sparklers altogether?
There was one or two.
New York,
California?
No.
California.
They banned the iron ones, not the wooden stick ones.
Yeah. Well, of course, the problem is, I was setting up a show once, and the audience had sparklers. This was in Salt Lake City, and everybody was lighting their sparklers and throwing them at the fireworks show. Makes you lose all your profanity. Apparently, in Japanese, hanabi means fireworks. Shinko means incense. So the early use of incense, they wrapped little incense powders up in paper, and they could burn them. And then somebody got the idea of using this particular mix, which doesn't have any steel or iron in it, you know. Now here's another thing, and I was very disappointed last night when I discovered that I brought a couple of these. I had planned to bring a couple of these devices. This was called a revolving wheel, but it's actually a Saxon. A Saxon is a revolving device. The fuse comes around, and there's an opening on one end and an opening on the other end, not on the very ends, but on the sides. And so they spin. This one's on a nail, but they actually gave you a little stick, so it was a handheld device. And they're gorgeous. And they use strictly carbon sparks. And the carbon sparks look like that Shinko Hanabi spark. So you can't buy these anymore. I don't think the Chinese export them anymore. But you occasionally come across some old fireworks, or you can, I don't know whether there's any made now, but this is called a flower pot fountain. And it's a choked fountain, but not a very narrow choke. And it's a strictly carbon mix. It's got some lamp black in it, a little charcoal, but no metal powder. And if it's just balanced just right, it produces that carbon branching spark, which is sometimes called the Cinco-Hanabi effect. So here we see how carbon sparks are formed. This again is a picture from the encyclopedia. So it's basically a slow burning black powder. It's got some other things in it, but not much. It's not a real complicated thing. It's no metal powders, and some carbon stays in the solution of the molten material, and it's protected from the atmospheric oxygen. And at some point, it comes to the surface and ignites and breaks the thing. So that's why you get branching. Titanium, wonderful pyrotechnic material. In fact, if somebody uses a lot of titanium, I kind of feel they're cheating because they can get beautiful effects without really working very hard at it. You take some ordinary slow meal powder, add 10% titanium, it's beautiful. But the distance the sparks travel is very much dependent on the size of the titanium. So in the top photograph, you see some 40 to 50 mesh tie, then a coarser tie, 20 to 30 mesh, and then at the bottom, 12 to 16. I used to make small titanium salutes, 1.5 inch diameter, and we found after a lot of experiments that a mixture of 12, 20 mesh tie, right near the bottom, and then some 40 mesh tie was optimal, because then you would get a dense ball of small sparks, but a spread, and a 35 millimeter film can, 1.5 inches in diameter, would, if I set one off from the roof here, there would be sparks that would hit the wall. And the salute was only 1.5 inches in diameter. And we used to shoot, 150 of those in a finale. Now, some other metals that we're going to talk about, I thought I'd show you a quick picture of them before we start to shoot them. We've got coarse flake aluminum, fine flake aluminum, looks just exactly like this, only you have to have more higher power to take a picture like this. So this gives you some idea for coarse, you have 1/10 of an inch. And flake aluminums can be very reactive. They're usually coated with an organic steric acid or styrene, which protects them from oxidation to a certain extent, but more importantly, it keeps them from sticking together. If you try to make flake aluminum without any styrene, you get lumps. But flake aluminum has been used since the earliest aluminums were flake. In fact, if you ask, how did they come up with making flake aluminum? Well, they had been using this technique of making metal flakes with bronze for hundreds of years. Icebound, you can buy these. It's nitrocellulose and titanium.
Is this in right here?
No, that is. There's titanium branching spark. Almost no smoke because it's nitrocellulose. Relatively cool burning. Put these on a birthday cake. Put them in a room full of people. You don't want to put your hand on the flame, but you can get your hand on the spark. And you see, that's not a very big tube, but it has a pretty nice long burn time.
Real tough, difficult. Sounds like a jet. Jet way up in the air.
Fans love it.
All right, Joe. Light the fuse and get away. Sound familiar? Yeah. What's going on there? Are those sparks? Or those are stars. But they're pretty unusual stars because they explode. And they're very much based on magnesium. But magnesium is unusual material. You can do things like this with magnesium.
Those are carbon sparks.
Yeah. Why does magnesium strobe so easily? The earliest strobe mixtures were made before they had magnesium. What they did is they mixed magnesium. You want to blow that out? What causes fire? If you want to make a fire,
Heat, fuel, and oxygen.
heat, fuel, and oxygen. But I can mix heat, fuel, and oxygen, not get a fire. You know, I mean, you have to have a lot of heat in one place usually. So most of us, when we make fire, we have a lighter or matches. You know, but there are fires that are said to be not caused in that way.
Fire.
Okay.
Yeah. That's water-activated flash sputter.
I'm taking a little bit different course here. I've discussed before how you can use flame moderators, and I said you can take magnesium stars and you can adjust the flame size and the character of the flame using graphite or using lycopodium powder. And I thought about some different things. I talked to a fellow at a Gem and Mineral Society show, and he said that the Scottish made black powder with anthracite, which that may or may not be true, but I thought I'd try anthracite. And this is minus 100 mesh anthracite coal. And you see it doesn't light very well, but you can see a few carbon sparks in it. And the thing is, there you can see it. If you substitute it for charcoal, it will burn. It's hard to light as a lump, but it will burn. And a little titanium in it. It doesn't light very well here, but if you make a typical charcoal star out of it, it will burn. This here, I wasn't entirely successful. I attempted to make coke out of this because Thomas Kentish in his book talks about coke grains. And you notice maybe that they're a little bit, it's hard to show, they're a little bit whiter, I think. You notice they're not quite as orange.
But see, when he used coke grains, he put them in gunpowder. So they got
So anyway,
heated up and thrown out.
It's hard to see it, but they're a little brighter. This is cellulose lint. Everybody has heard of nitrocellulose. This is just cellulose. It doesn't make sparks, but it does. You can see some, orange flame coming from us. This is like very, very finely shredded paper. You notice it does have some characteristics that are a little bit like nitrocellulose, that it is a flammable material. You can kind of see that it does do something. And here's another carbon-containing material. This is just wood meal. And it has a lot of resin in it. So you can see that it ignites more easily and the sparks are a little more long-lasting. Or, I would say they're not embers because there's rosin burning off. If you look at this under a microscope, it's quite glossy and shiny in spots. And you see the wood meal makes better sparks than the cellulose does. And this is atomized spherical titanium from a metal plasma cutting process. And you'll notice it's sparkling and branching, but it's not porous at all. It doesn't have, what is this? Too cold.
There you go.
Yeah. So that's spherical. There's no sponge characteristic to it at all, yet it still sparkles. This is zinc aluminum alloy made up kind of like a granite zinc star. And you may notice kind of a bluish cast to the flame.
Here's my torch.
Yeah, let me see if I can get this to work. So you notice there's a bluish cast to it. But it's a zinc aluminum alloy. And then this one is your standard original Pyrotechnica #1 glitter mix.
2.
No, the one with Fink Bone. The very first one.
Oh,
The little pamphlet one
yeah.
that Jim Finkbone had some things in, and this was the first one I remember being published. It's 49 potassium nitrate, 9 aluminum, 9 sulfur, 9 charcoal, 9 antimony sulfide, or 9 sodium oxalate, and 5 dextrin. And you notice it pulses and glitters just a little. You can see it in there. It glitters just a little bit. But that's zinc aluminum alloy. It's not pure aluminum. So that's just...
But, I want to point out that's not a fair test of that star because there was a lot of stuff that came off it that hit the rock and cooled. And if that star had been falling through the air, there might have been a lot more visible stuff.
So this is basically a charcoal star with aluminum added to it. And you'll notice that the sparks will look like charcoal, but they're brighter. So they're a golden color spark, but they're really made from aluminum. And then...
And aluminum sparks can burn at all different temperatures.
And then the thing about sparks is they may be thrown out as solid objects, or they may melt and burn independently. So this is, I'm making sure I got the right one. This is Weingart's wonderful cinder star, except it's made with potassium perchlorate and guanidine nitrate instead of barium nitrate. And you notice it was kind of breaking up and dropping little pieces. And then this is Ron Lancaster's silver star from his 4th edition, which is uses magnesium to make it burn, and it has 2 sizes of atomized aluminum. See if you can see the difference in the sparks with this as it throws out the atomized aluminum. You see how these little balls are flying out of it? Should I do it again?
Yes. Two of them.
Put it up on the bucket.
Okay.
Joe, put it on a stick and hold it up.
Or put the rock on the
Advice
bucket.
from the audience.
Okay, that's a good idea. Put the lime in the coconut.
Precision rock.
Flat rock. The rock we were trying to find.
Yeah, really.
Oh, wow.
Okay, so there you can see the shower of sparks. And then this one is the same thing, only it uses flake aluminum, minus 30 flitter aluminum. And you'll notice that there isn't a whole lot of difference because either way it melts and burns afterwards.
That's the aluminum like I showed you a picture of. The flake.
So that's the end of my part of it, but the point I'm trying to make here is if a spark is thrown out as a glowing particle and it burns as a discrete object, it will retain its original characteristics, and it may branch or it may have an elliptical shape as carbon sparks sometimes do. And then if it's a type of cinder star, there are formulas for silver stars that may be only say 40% or even 30% potassium perchlorate, and the rest is all aluminum. And they will melt and throw out glowing liquid droplets, and that's what's generally referred to as a sinter star. And they have this drip look, and fall sticks oftentimes have that kind of look to it. So I was just trying to illustrate the difference between some of these things, and the different, some are gold, some are light gold, some are brilliant white, and so forth. So that's that. Thank you.
All right. How much time do we have left? What time is it?
Almost 10 minutes over.
Huh?
You're almost 10 minutes over.
Keep going.
All right. Well, then in that
Keep going.
case.
Keep going.
Is this cool now? I want you folks to see, can you identify what this is? Little pile, about as big as your thumbnail. Light it from that side, I don't want to stand in the way.
Sorry about how loud it is. It's barely across that.
Ready? What was that? That was meal powder.
Yeah.
Alright, now I got a few things we can do. I got a million things to do, but this should be good. No. All right, this is pure copper powder. It's atomized. It's just elemental copper. There's nothing else with it. And to tell you the truth, I don't really know what it'll do. It's contaminated with other stuff on this cardboard.
Just turn it over and piece it the other way.
What color? Green. But I thought copper made blue. There's no chlorine. Take a copper wire, hold it in a flame like this, you'll get a green flame. But you don't ever see pyrotechnists using pure copper to make blue flames because it's not a vibrant green. It's not like a barium green. Well, I got 275 more bottles here. I've got some really exotic stuff. Let's try this. Where's my cardboard? Here. Oh, here. I'm not going to tell you what this is until after I do it.
Name that.
Not very ignitable, is it? And yet, what I just blew in that flame, when it's made a few little sparks, has killed many people and caused enormous damage. It was wheat flour. And if you have enough of that in the air with dust, it's an explosive mixture. Dust explosions can be really, really bad. Put the lid on that for me if you can find the lid. All right, let's see what else I can find here that's. I got some vermiculite.
Lids are both over there.
It won't do anything at all. So I'm not going to bother with it. Thank you. No, I appreciate that.
Yeah, the lids are both over there. I don't know which one went to which bottom.
They're labeled on the lids. All right, I'm going to throw this out and ask you what you think it is. Take that away. Where's the cardboard?
Cardboard is right here, sir.
Thank you. This is, I'll give you a hint on this stuff. Very, very reactive, but not used in fireworks very much. That's pure magnesium. Try some of this. I really don't know what this will do. I found it in my collection. This is ferrosilicon, alloyed between silicon and iron.
How much of that do you have?
Oh, there must be.
No, I mean not all together. Is that
No, I just have a little bit.
okay?
I have a maybe a quarter pound or less,
Okay.
and I've never experimented. This is the stuff that
The Shimizu talks about.
Shimizu talks about making a what he calls red thermit powder.
You
And
know
it,
the approximate percentage of the iron and silicon?
no, it came in a bottle labeled ferrosilicon.
But apparently it's a big thing in steel making. So
Yeah.
if you know somebody who works in a steel mill, you might score something cheap.
There you go.
It should be metal, right?
If it can go wrong, it will.
Just there.
Huh?
You cut another flap off your box, maybe?
Sure.
I was wondering. Yeah, I was wondering if
Sometimes it's air. It used to be like
I can tell you folks are all devoted pyro because there's not many people who would sit and watch sparks on a flame for an hour and a half.
That's a nice floor up there, so I guess if you're burning
Yeah.
other items,
yeah, campfire
that's
goes.
a
new chemicals.
before I can go.
You never know what you're gonna get.
Winokur doesn't know what the fuck this is. I don't know what it is either.
Titanium TI.
What's that say? Tell me.
It's also labeled on the side of the bottle.
Oh, well, what the hell am I looking at the lid for?
MC/AL 6535 300.
Magnalium 6535.
Oh yeah, I don't know what the hell it stand for.
Or blend.
Jan M45 military. 65 magnesium, 35 aluminum.
Did you have some of that, Joe?
I have some, but it's gotten, I didn't bring it, it's gotten dark.
Oh, and you didn't bring it, no.
Yeah, something the military uses that doesn't corrode as fast as mag. Joint Army Navy magnesium. -40.
Where's the squirt bottle?
From my spray can.
Right there. On the table.
Right behind you, sir.
Well, that,
Right behind
This
you.
is the one that's still.
That one might not be cold. The one here
Well,
might
it's
not
all
be-
right. It's okay if it's cold, as long as I don't tip it upside down.
This is brand new.
Yeah.
There you go. Just throw it in there.
It's sparkling.
Now, here's the question. The trick I did with sparks, I was going to do it, but I didn't get a chance to do it right. I got some zirconium powder that's really fine. Now, zirconium powder that's really fine is pretty hazardous. It's pyrophoric. Anyone know what pyrophoric means?
Sometimes wait for an ignition source.
Huh?
Spontaneously flammable.
Yeah. Bruce got it exactly right. It's spontaneously flammable in air. So if I had a high pyrophoric powder on this piece of cardboard and I went like that, powder would go in the air and it would ignite. Not because there was an ignition source, but because the stuff is so reactive and there's enough oxygen in the air. And there aren't too many things, fortunately, that are pyrophoric. And if they're pyrophoric, you can better believe they're not used in pyro.
Can make pyrophoric iron.
Yeah, iron, if it's really fine, is pyrophoric.
Lead.
Yeah.
Yeah, some metals, but they have to be really fine. Well, zirconium, when it's really fine, you keep it wet.
Supposedly, if you ball wheel magnesium,
Yeah. Well, here's some zirconium powder that I've had for years and years, but it's in water. If you dry out a little bit of it, I used to just take a little scoop, dry it out, and then when it's pretty dry, you can handle it. You just don't disperse it in the air.
yeah.
And I would put a little bit on my finger, and then I would stand in front of a fireplace like this, with my arms folded and titanium here, and I would do this. I would aerolize the zirconium, but it wouldn't ignite in the air, but it was fine enough that it was drawn into the fire. And the reason I thought of that is, you notice when we did this, there were sparks, and they kept going. Even after I backed off and I was done fooling with the cardboard, there were still sparks there, and that's because some of the really fine particles don't ignite, and they get carried up in the flame, and then they fall back down again, and they ignite. And in a fireplace, that works really well. So you can say to somebody, "What's going on with the fire?" And they look and say, "I don't see anything going on." The fireplace starts to sparkle, and they say, "What are you doing?" And you say, "I don't know. I walk away," and it's still sparkling, you know. And so you can play around with stuff like that, but I have to warn people: zirconium is pretty hazardous, and it's now coarse zirconium works very much like titanium, and I have some zirconium sponge, which is like 12 mesh or something. And you can put that in a solute, and it looks like titanium, only it's even brighter.
I wonder if hafnium would be even more reactive.
I don't, you know, there's a fellow at the Class C tent that usually has some bags of hafnium, but it's turnings.
That's Camel.
He had some finer stuff this year.
Did he?
It's very hard to light. Very, very hard to light. The military has experimented for some reason, I don't know why.
Okay, here's one we should do.
Well, uranium's supposed to be pretty expensive.
Oh, yeah, I bet it is.
Huh?
I bet it is.
Yeah, I know a guy that made uranium
That's
fountains.
one. Uranium fountain.
Yeah, he took coarse uranium metal, 238, and
They still burn hot though.
oh yeah,
Well, that's why they,
No, they burn hot.
Fountains.
those uranium bullets, when they hit a tank, they just disintegrate into sparks on the inside as they go through the armor.
Yeah, I was told by a military guy they penetrate the turret on a tank and ricochet all over the place throwing sparks.
all right. What do you think this is? Zinc. Yeah, that was pure zinc, and it doesn't ignite very well. But you can make some pretty beautiful stars with zinc if you do it just right. But the chemistry of zinc stars hasn't really been studied. There's a rather well-known formula referred to as a spreader star that uses zinc. And I made them. You get a little tiny star, and you light it, it just explodes pieces of burning zinc, which then break up all over the place. It makes a horrible mess. But they're not very bright. They're interesting. I've seen at PGIs, and I think even somebody here at the Winterblast once made some zinc spreader star shells. And it's a kind of a weird, the shell breaks, and then what the hell am I looking at there? The stars come out and they kind of move around, and they have that slightly bluish
Heavy
tint.
shells.
Huh?
Pretty heavy shells.
Yeah, and the thing is with the zinc is so heavy that it's not, you know, it's not used much.
Use zinc stars in his big rockets.
No, they use zinc fuel in rockets.
No, stars in the heading of his big
Oh, really?
rocket. Yeah.
Well, yeah, you can do that, but you're far away. See, that's one of the problems. Is
You can still see that unique color.
yeah.
As long as it's not anything that's brighter that draws it out.
Let's see what else I have here. I think I have some other exotics here that we probably should look at.
Let me just throw this in. At some displays, I think some of them were Aaron Mayfield's. I don't know. I think they were Chinese shells, but they seem to be kind of like a lamp-black tail and a zinc point on them that broke up. So I think someone in China has made them for somebody at least once.
Joel, let's try this. I have no idea what this is going to do. Let's use this side.
It's always encouraging.
Yeah, cornstarch.
Box there.
And that's lacquer dust. Looks like gas.
That one I don't think is open.
That's not really corn.
That's cornstarch.
Corn.
Yeah, a lot like Lycopodium, but not as fast.
Yeah, kind of like Cremora.
It's gonna start smelling like dextrin.
You know, I have some lycopodium here somewhere.
Yeah, that'd be great.
Help me.
That's why I didn't bring any.
I can't read it. Wood meal, you already did that, right? Powdered sugar, let's try that too.
Starts smelling like caramel. Burnt sugar.
You know, I was thinking about red gum, but it's so resiny that I didn't think it would be very interesting. Probably make a yellow flame, you know. How many of you know what lycopodium is?
Insect.
Most of you don't. Okay. It's the spore of a moss-like plant. The name of that plant is, are you ready? Lycopodium. And the individual particles are relatively spherical, and they contain a lot of lipids, but they're very easily ignited. And in the days before aluminum powder and magnesium powder, they were used in theaters to make big flashes of light. They didn't have flash powder. Closest thing they had was lycopodium powder thrown into the air and an ignition source.
Have you ever used the upside down funnel to disperse like that Winokur shows?
Yeah, there's a picture in Weingart that shows what they call the Lycopodium pipe. And apparently in the 1800s, when they wanted a big flash of light on stage, they would aerialize the Lycopodium and have an ignition source, sometimes blow it into a candle.
Well, in The Wizard of Oz, when the witch appears, you see the big flame, that's Lycopodium, then the big, like, gasoline-like flames on either side of the wizard image. When the, the four of them approach him, this great big flame, that's Lycopodium. A lot of it.
Oh, is this looking?
There.
There we go.
Well, Amanda was selling it.
Let's try this. This is powdered sugar.
Can you mix the Lyco with any of the other chemicals to get a color? Effectively?
It'll be yellow. It's sometimes they refer to lycopodium as vegetable sulfur. So it would be used as a fuel. And every once in a while, if you read a lot of pyrotechnic literature, you'll find a formula.
Did you do any sulfur here?
No, I've got some.
Okay, well, I'll make a nice blue flame.
It does. Well, maybe.
Weingart has a silver star.
Weingart has a silver star that has lycopodium powder in it, and I thought it made it perhaps more ignitable, but it must be a heck of an insulator, because actually if you put even a small amount of lycopodium with the magnesium mix, it'll slow it down. You'll keep it from burning too fast without changing what it looks like, but it doesn't take very much.
But back to the lycopodium moment, if there's any kind of sodium, it just drowns out the other colors.
Yeah, but there's a lot of carbon in lycopodium, and oils and things, so that's what makes it yellow, I think. I don't think it's sodium.
You ready for the sugar?
Sure.
Sweet.
It's powdered sugar. Not as ignitable.
Did we do this before? We might have already done this. This is coarse zirc.
No, you.
Zirconium.
What form?
Oh, sir.
No,
Not light.
yeah.
Really? We'll talk to it.
Light!
It's gone.
The stuff I have back here.
and stuff. That's the sugar.
I think that was an anvil.
Now, tell me, what do you think that was?
Loud.
What? I can't get the lid off this. This is titanium hydride.
Somebody's truck was laying on the ambulance.
Maybe yours is finer than mine.
That's a shotgun.
It's almost like an embolism.
Titanium hydride.
That's what that was you just sent up, was titanium hydride?
Yeah. So titanium is exposed to hydrogen, it gets real brittle. And some of the hydrogen stays on it. They can get rid of some of the hydrogen, but some of it is bound. And it changes the properties of the titanium. And if you could get titanium hydride in the coarse form, I think it'd be very useful in pyro. Coarser, if you could get.
You get zirconium hydride.
Yeah, I couldn't. I have a little container of zirconium hydride, but I couldn't find it.
That's one of the trouble they have with rockets. You're trying to use liquid hydrogen fuel, and the hydrogen likes to absorb everything.
I still can't read this. Iron fine. You did some of that.
No, not iron. You said you had it.
I do. There it is.
Sand.
Oh, what a delicate effect.
Is that very fine iron?
Yeah, fine iron. Yeah.
That's why it's great.
That was cool.